Hey, my name is George Shakin, and today I wanted to talk to you about a recent preprint I put on the archive titled On Higher Energy Decompositions and the Sum Product Phenomenon. Before I start talking about the results in this paper, first I wanted to outline some of the history in the area. It's common in combinatorics that the story starts with either Erdős or Szemerédi, and in this case it's both of them. In their paper, On Sums and Products of Integers, they introduce the main conjecture of the area and make partial progress towards it. So let's take a closer look. They consider a sequence of n integers that is a set of size n. In equation 1, we can see they consider all the possible sums and products of these integers. In the very next line, they say, it is tempting to conjecture that there are more than n to the 2 minus epsilon distinct integers of the form 1, that is, n to the 2 minus epsilon sums or n to the 2 minus epsilon products. So that's basically as many sums or as many products as possible. The idea is that there is no set that can have both additive structure and multiplicative structure. For instance, an arithmetic progression is a set with a lot of additive structure, but doesn't have much multiplicative structure. And similarly, a geometric progression is a set with a lot of multiplicative structure, but little additive structure. Now they say, we are very far from being able to prove this. And even today, we're still far from being able to prove this. However, in Theorem 1, they made partial progress towards their conjecture, showing that the number of sums, or the number of products, is at least n to the 1 plus c, for some fixed constant c. So here's the Wikipedia article on the Erdős-Szemerédi sum product conjecture. So here's the conjecture stated in a little bit more modern language. And so the question is, can we take epsilon arbitrarily close to 1? And so I'm going to talk about, for a little bit, the kind of current progress towards this and what quantitative bounds we've had for epsilon. Nearly 15 years after the original paper of Erdős and Szemerédi, Melvin Nathanson wrote on the subject in his paper titled On Sums and Products of Integers. His starting point for the proof was their original paper, which he modified. So pretty soon after Nathanson's paper, my advisor, Kevin Ford, wrote on the subject. So we can see in the title that we changed the focus to real numbers instead of integers, which was in the title of the previous two papers. So it was at this point that there was kind of a switch from thinking about integers into thinking about real numbers, and that's kind of the way that things are today. So there's a funny story about this paper. So Kevin and Melvin were at a conference together, and Melvin goes to Kevin and says, here's a draft of my paper, why don't you have a look? So on the plane ride home, Kevin takes a look at the paper, reads it, and by the end of the plane ride already has an idea about how to make an improvement. So let's take a quick look at what Kevin proved. So his main result is in Theorem 1, and he proves that the exponent 1 over 15 is admissible in the sum product conjecture of Erdős and Szemerédi. So pretty amazingly, within months of Ford's paper, Elekes released this, also in memory to Paul Erdős. So here he introduced completely new ideas to the problem, and this kind of marked the beginning of kind of modern progress towards the sum product conjecture. So Theorem 1 is Elekes' main result in this paper. He's able to show that the exponent 1/4 is admissible in the sum product conjecture. So the amazing part about this is his paper is only 3 pages. And here's one of the pages. So his new idea was to use the Szemerédi-Charter theorem from incidence geometry. This was the first time that this theorem was used in the sum product conjecture, and it was very impressive that he was able to come up with this argument. So incidence geometry has since then played a big role in the sum product conjecture. After Elekes, another Hungarian mathematician started writing on the subject. So in this paper, Solymosi was able to show that 1/3 minus epsilon is admissible in the Erdős-Szemerédi sum product conjecture. So this paper is pretty amazing in that it's completely elementary and really elegant. He's able to use just elementary geometry to obtain this sum product bound. So he gets rid of the use of the Szemerédi-Charter theorem from Elekes' paper. And so this result also has played an important role in all future works on the sum product problem. Solymosi's argument was the world record for about 6 years. And it's kind of amazing that his quick elementary argument remained the best known bound for the problem for such a period of time. Konyagin and Skretov were able to improve upon Solymosi's result by c, where c was some small fixed constant. The argument from this paper left the realm of being short, as in Solymosi and Elekes' argument. Nevertheless, their argument is still very nice, and it combines many ideas from additive combinatorics. So here's their second paper on the subject, where they claim 1/3 plus 5 over 9,813 is admissible in the sum product conjecture. So if you're new to the area, you might think, where the world is that exponent coming from? It's coming from an earlier paper of Skredov, so let's take a look at that. So this paper of Skredov plays an important role in the Konyakin-Skredov argument, so let's take a look at a particular theorem that they find useful. So here's Theorem 11 of the paper. It turns out we only care about the case alpha equals 2, so equation 17. So we have that lower bound for the sum set, and on the right-hand side we have some crazy exponents, notably the 21 over 37 and the 79 over 37. So those crazy exponents are used in the Konyakin-Skredov argument, and that's what kind of gives rise to their 5 over 9,813 eventually. This is one part of the argument that I'm personally not sure is optimal and could possibly be improved. Finally, we have this recent paper of Runev, Skredov, and Stevens, where they're able to show that 1/3 plus 1 over 1,509 is admissible in the Erdos-Semerity sum product conjecture. So they prove a few things in this paper, and one of their kind of main topics of study is this energy decomposition result of Bolog and Woolley. So let's take a look at that paper. So here's the paper of Bolog and Woolley, a low energy decomposition theorem. So in this paper, they introduce a new conjecture related to the sum product conjecture. So here's the main result of the paper, Theorem 1.1. It basically says that any set can be decomposed into two sets, one of which the additive energy is small, and the other of which the multiplicative energy is small. Right after that theorem, they say, this theorem shows that any finite set of real numbers can be split into a highly non-additive part and a highly non-multiplicative part. So this was the first time this kind of way of thinking of the problem was introduced into the sum product conjecture. Indeed, it's like an energy analog of the sum product conjecture. So going back to the Runev, Skredov, Stevens paper, one of their goals was to quantitatively improve the best known bounds for the Bolog-Woolley decomposition. So here's the main result of their paper, a quantitative improvement of the Bolog-Woolley decomposition. I should mention that the Theorem 7 has nothing to do with their sum product estimate, and in fact, the sum product estimate follows from a different decomposition. So here's another theorem of their paper, Theorem 12, which turns out to be another decomposition result. If we look at equation 10, we see that we have the multiplicative energy times the additive energy with a skew towards the additive energy. So if the additive energy of C is large, say about the size of A cubed, then the multiplicative energy of B has to be small, about the size of A squared. It turns out that this is a key lemma in the Konyakin-Skredov argument, and this improves what the Konyakin and Skredov used originally. So that's how they get an improvement on the sum product estimate. So let's take a look at my results. I'm able to make slight improvements to the Erdos-Semerity sum products problem, as well as quantitatively improve the Bolog-Woolley decomposition. So here's the first theorem I claim, a slight improvement to the sum product estimate. I mentioned that I'm almost able to improve Sholomonoshi's exponent by 1 over 1,000, so we're almost in triple digits in the denominator. So let's take a look at Theorem 1.10. I'd actually consider this the main result of my paper, and really the Bolog-Woolley decomposition is a consequence of this theorem. Anyways, let's see what it says. So it says I can decompose a set A into two subsets that are large, as in condition 2, such that this condition 3 holds. Basically it says that X has no additive structure and Y has no multiplicative structure. Now, what is this D plus of X? So D plus of X is bounded from below by 1 and bounded from above by X. And it kind of behaves like additive energy, in the sense that if the additive energy is small, that means X has no additive structure. So similarly, if D plus of X is small, that means X has little additive structure. Actually, D plus of X can really be thought of an additive energy, but a third moment estimate in place of a second moment estimate. So here's the definition of D plus and D times, and we can see on the right-hand side we have this third moment estimate as opposed to the second moment estimate of additive energy and multiplicative energy. So you might ask, why in the world are you studying third moments? Well, it turns out that from Semerity-Trotter all the way back to Elekish's result, it turns out nowadays we can see this as a third moment estimate, and so it makes sense to study third moments. The quantity D plus of A originated in a paper of Schoen and Skredov, where they tried to make progress towards a conjecture of Erdos. So Erdos' conjecture is about convex sets, and basically he conjectured that the sum set should be large in this case. So Schoen and Skredov were able to make world record progress towards resolving this conjecture, and actually this is still the world record to this day. here in the preparations, we can see they're introducing the third moment analog of additive energy. It turns out they're not introducing d plus and d times like we do today, but they're using the same ideas. So let's take a quick look at this part of their paper. So here they're showing that if d plus of a is small, then a minus a is large. So this is maybe what an argument might look like for such a result. So what's in this paper? So you might notice I have a long intro, about 8 pages. So the reason why I wrote such a long intro is because I'm trying to give as much motivation and intuition as I can for these quantities d plus of a and d times of a, which play a really important role in the entirety of the paper. So in the second section, I prove what I consider my main theorem, and in the third and fourth section, I prove various consequences of that theorem, which I mentioned in the introduction. The final section is reserved for the sum product estimate. There I state and prove a few results of my own, and then sketch the entirety of the Quinag and Skretov argument to see how my pieces fit in. That's all I have to say about this paper right now. Don't forget to hit the like button, and subscribe if you want to see more of my math videos. Anyways, thanks for watching. I really appreciate you guys taking time to see what I've been working on lately.